I had not intended to continue this series on digital modulation, but after reviewing the applications video and looking back at the earlier two, I realized that I had left a couple of issues pending, and I had misled everyone in one section, and I wanted to correct all of those, or at least to the extent that I can. What's on the screen is the YouTube channel by a professor, David S. Ricketts. Earlier I mentioned that when we got to pulse filtering that I would tell you about his channel. This is module 5 of what I think is a 13 or 14 module course on digital modulation. This particular module is on bandwidth and pulse filtering, and I wanted to point this out because I said when we got there that I would mention this channel, and then I never did, but it also reminded me that when I was referring to the raised cosine filters and the Nyquist filters and so on, in other words the baseband filters, that I actually mischaracterized the way that the filter shape varies with alpha. So I'd like to also cover that. But I would like to recommend that you take a look at this channel on YouTube and these modules. They're very valuable. What I'm going to be talking about for the next minute or two is the ability to restrict the baseband using a particular filter and the effects that has on the final modulated signal. But take a look at these. I think you'll find that these videos, at least I found them very helpful, and I think you will too. The typical filter that results, normally a non-digital filter, is often called a Gaussian filter because it has a shape that is similar to the Gaussian distribution curve, that is the normal distribution curve. There is a type of filter that was originally proposed by Nyquist that is sometimes referred to as a Nyquist filter. It's sometimes referred to as a raised cosine filter or a root-raised cosine filter. And basically, the filter is an attempt to shape the bandpass so that you get a certain effect on the occupied bandwidth of the resulting signal. And that is done by adjusting what is called alpha. Now, if alpha equals 1, you get the basic Gaussian shape. In an earlier video, I think I said if alpha is 0, you get Gaussian, and that's backwards. It's alpha 1. As you lower alpha, the tail begins to move inward until eventually, if you have alpha equal to 1, you get what some people call a brick wall filter. In other words, a filter that just completely cuts off at one frequency and passes nothing else above it. The occupied bandwidth of the resulting signal is a function of alpha. So as alpha goes to 0, the occupied bandwidth goes down. With a Gaussian filter, the occupied bandwidth is 2 times the symbol rate. In other words, alpha equals 1, so 1 plus 1 is 2 times the symbol rate. And that's why that, for example, you see that your IF bandwidth when you're doing digital demodulation is twice the symbol rate, because it assumes this Gaussian shape. If, however, you have a Nyquist filter, say a raised cosine filter, then alpha is less than 1 and the occupied bandwidth goes down. I also wanted to answer a question that a student asked about why in the videos I emphasized the transitions through the origin quite a bit. And the reason for that is, particularly when you're doing frequency or phase modulation, the discontinuities in the waveform, in other words, the places where there is a steep, essentially infinite slope between one part of the waveform and the next, are the ones that cause the most trouble in digital communication channels. As a result, there have been many attempts over the years to find ways around that problem. One of the ways is through the coding methods that we talked about in concepts and in applications. An area that I didn't talk about, but actually is rather important, is the idea of coherent frequency shift keying. Now, if you remember, frequency shift keying is simply a signal in which when there's a zero, the modulator puts out one frequency, and when it's a 1, it puts out another. This shows a very smooth transition between the two. However, this transition can be anywhere from smooth like this to a transition from this point instantaneously to this point, depending on the relative phases of the signals. So let's suppose that you have two oscillators, one running at this frequency and one running at this frequency. And all you do is you simply shift between those. Maybe you have a gating system, a gating circuit, that you bring this one in when it's a 0, you bring this one in when it's a 1. Well, if these two signals are not coherent with each other, you can get very large instantaneous transitions in the wave. That causes difficulties. And one of the ways that you can try to solve that problem is to use a method called coherent phase shift keying. It's also sometimes called minimum shift keying. And so I'd like to talk about that a little bit and maybe illustrate one of those on the vector signal generator. There are other ways that you can attempt to keep the symbols from having those sharp transitions. One of them is by coding the modulation in a system called gray code. I won't talk about this very much, but if you are interested in this area, you'll want to look at the idea of using gray codes to minimize the instantaneous changes. Another way is called differential phase shift keying, and in that you code the constellation in a way that you only change one symbol at a time. And you'll see this in a little bit because there's a relationship between this and what I am going to show you, which is minimum shift keying or coherent frequency shift keying. This is a gray-coded version of what I just showed you. And once again, it's to minimize the number of symbols that are changing or the number of bits that are changing in each symbol as you transition from one symbol to the next. You may remember when I showed you this diagram in an earlier video that we talked about the advantage of shifting the transition points for the I and Q signal so that you avoid the origin. The idea of MSK is to do something similar to that. That is, this shows a typical frequency shift keyed signal. In MSK, what you are trying to do is to actually get the carriers, that is the mark and space frequencies, to be phase coherent, so that when it shifts from a mark to a space or a space to a mark, it does so at a time when the two signals are at zero. In other words, a zero crossing interval. What that tends to do in the constellation diagram is to actually group a series of symbols around the symbol rate here, so that, as you'll see when we display this on the scope and on the spectrum analyzer, there will be a grouping of symbols. Here is a conceptual description of what we're going to be trying to do. Up here is a typical MSK, or a typical phase shift keying, in which the phase shift is, or the frequency shift is not coherent. And as you can see, there are sharp transitions, like this one there, one there, when you make transitions from one frequency to the other. As I pointed out, those are something you'd like to avoid. Well, you can avoid that if you adjust the mark frequency and the space frequency in a way that they have a relationship to one another, where one, for example, is the baseband or bit rate times 1.5, and the other one is times 2.5, so that you'll see that the transitions, that is between a 1 and a 0, or a 0 and a 1, the transitions in frequency occur when those two frequencies are both at zero amplitude. Now, to do that, these two signals have to, of course, be derived from a common oscillator, or at least be linked together by some method. So we're going to look at MSK in a second, and how it looks on the constellation diagrams. One reason that I'm talking about this is MSK and what is called GMSK are used in the GSM system. The GSM system is the system that is used, for example, for 2G in the United States by companies like AT&T, and throughout Europe for the 2G and parts of the 3G networks. So it's an important method. The difference between MSK and GMSK is simply whether we use Gaussian filtering on the baseband. And that's one reason I introduced this by going back and talking about Gaussian filtering. So enough additional theory. Let's get on and do something with the hardware. On the Triarchy generator, I have set up a coherent frequency shift keyed waveform, sometimes called minimum shift keying. And I'm going to zoom in on the I and Q waveforms to point out that if you notice when for example, the Q waveform changes frequency, it's at the point when it is at zero, and the opposite, or I signal in this case, is at a maximum. Similarly, the I signal changes its direction when it is at zero. Let me show you in the constellation diagram what that does to the signal. What it does is produce the circular pattern that you see here. Now, we're running a symbol rate of 36 kilohertz, and over on the spectrum analyzer, we have in the lower left the I diagrams, we have the spectrum plot, but more important, you have the constellation diagram. And notice that by making the phase changes coherent, or the frequency changes coherent in an MSK signal, you restrict all of the symbols to this outside ring. That is, if you'll notice, the black lines, remember, are the transitions. And occasionally there is an error and a transition occurs through the middle of the circle. But almost all of the transitions occur on the circle itself or very near to it. This is one of the characteristics of an MSK signal. Now, I referred to the fact that there is an improved version of MSK that is called Gaussian MSK, or GMSK. So let me change the setup to show you what that looks like. I've changed the vector signal generator to generate a Gaussian MSK signal. Notice now that, as we pointed out earlier, the symbols that are transmitted statistically are grouped in these 45-degree quadrants. That is, around this point, you see most of the symbols are in this quadrant, or around this 45-degree point, here and here. That is accomplished by adjusting the baseband using a Gaussian filter. And this is the actual raw data that is applied to the I and Q modulators to produce that Gaussian effect. Now, when you're working in the digital domain, there really isn't any distinction between digital filtering and any other kind of digital signal processing. So what has happened here is that this signal has been processed so that it produces this characteristic in the constellation. So now let's go over and look at what it looks like on the spectrum analyzer. You see here this is the spectrum plot, and this is the constellation diagram. Now notice here that it's a little bit hard to see, but basically what happens is these bits tend to be grouped together so that frequency transitions that result in phase changes are grouped around these 45-degree points. What I'm going to do now is compare the occupied bandwidth of these two signals so you can see that, and then hopefully wrap this up. Here is the occupied bandwidth plot on the SignalHound spectrum analyzer. Let me zero in a little better on the actual figures. You will see that the occupied bandwidth is 32 kilohertz. Remember, we have a symbol rate of 36 kilohertz, and we're using the 99% occupied bandwidth. So basically, we are able to concentrate 99% of our power in a bandwidth, or an occupied bandwidth, which is actually narrower than the symbol rate. Now let's look at the MSK signal and see what it reads. Here is the MSK occupied bandwidth. Now remember, this is without Gaussian filtering. And you notice that it's occupying 42 kilohertz at the 99% points. The lesson here is that by proper filtering in the baseband, by using a Gaussian MSK signal, you can do frequency shift keying in ways that not only lower the occupied bandwidth, but also reduce the inter-symbol interference, as well as reduce the error rate by causing the frequency changes to be phase coherent. Now, for reasons that are historical rather than technical, that method of doing things, that is, the using a phase coherent frequency to generate marks and spaces, and then applying a Gaussian filter has been called minimum shift keying. And there is some basis for that, but I frankly think it's a little bit misleading. I prefer to refer to MSK as phase coherent frequency shift keying, but use the terms that you find most useful. I hope that this series and the demonstrations of how the SignalHound SA44B and the Triarchy VSG 6G1 work, and some of the capabilities. I have nowhere near demonstrated all of the capabilities of these two instruments. Perhaps I will do some additional videos on those in the future, but at this point I think I have sufficiently confused digital modulation, and I'm going to then move on to something else. So in the meantime, have a nice day.